Oh, hi, you're here.
Hi.
Okay, sit down. So, did you have a good day yesterday?
Yeah.
Did you have a chance to look at your book? Okay. Let me see your book because for the most part, we'll be working off your book. Okay. All right. Okay, so is the thing becoming a little bit fun? Is it making a little bit of sense?
Yeah.
Okay, I'm glad to hear that. Because geometry, the funny thing is, at every level, a lot of students, a lot of kids used to like math when they were in elementary school. But then when they get to middle school, it seems like each year a certain number of people drop off and don't like math anymore. You see a really big change when you get to algebra. A lot of kids who were really good in math, all of a sudden they're not good anymore, and they don't like it anymore when they get to algebra. Then there's still some who like it, and then when they get to geometry, because of all the proofs and all the theorems and all, it's a lot of information to take in, and a lot of people drop off. And, I'm hoping that by having these study sessions, you'll be able to maintain your interest in math, and that you'll see that it's not that bad, that it's actually fun to solve these math problems, and that some of the things that we learn here will be useful in other courses as well as in life, okay? Because as I said before, geometry really emphasizes reasoning, logical reasoning, and thinking straight. And that's useful everywhere in life. Okay, I think you'll recall that at the first session, we had three goals. One was to learn how to read definitions and theorems and statements from your textbooks. Read it and understand it so that you won't need someone explaining it all the time. Okay, and also because I hear this complaint often that students don't understand what their teacher is saying, that the teacher just teacher just blazes through the material. So it's to your benefit if you know how to pick up your book and read this stuff and understand it on your own. Okay, so that was one of our goals. Another one of our goals was to expose you to proofs and to get you thinking in that structured manner, that very logically tight, systematic, step-by-step way of thinking that you need to think to be able to do a proof. Okay, and again, that's useful in life. Okay, and the third thing, if you recall, was that I wanted to teach you how to solve any problem. I wanted to teach you how to solve problems you haven't seen before, just by taking basic principles and proceeding in a step-by-step fashion. You should be able to solve 90 and 95% of the problems that you encounter. And that way you don't have to memorize different sample problems or example problems in your book just to be able to do well on a test. That's not the right way to do it. Okay, so so last time we talked about reasoning. We talked about inductive reasoning, right? And we also talked about deductive reasoning. And we spent a lot of time on deductive reasoning because geometry is basically about deductive reasoning. And so if I could I'm going to sketch this little diagram that sort of represents how deductive reasoning and how geometry uses deductive reasoning. Okay, so basically a typical geometry situation, you have some givens. Okay, you have some givens. These are facts, the givens of the problem. They give you certain facts, and you take those givens and you plug them into this sort of a bunch of, I would say, for the most part, conditional statements, okay? But it's more than that. You plug it into this logical reasoning machine, okay, which has theorems, postulates, theorem, postulates. It has definitions and undefined terms. So you plug this into here, and then the output is some conclusion, okay? Some sort of statement. Either some statement, or some measure that an angle is equal to 50 degrees, or that two lines or two line segments are congruent. Okay, so, step one is the given. Step two is all the logic, all the reasoning, taking, if this is so, then that is so. That goes in step two. And then after you've put all those conditional statements together, and along with definitions and so forth, you end up with some sort of conclusion. So that's the structure. Okay, so that's the structure of deductive reasoning. Okay, so again, you take these givens and you put them through different theorems and postulates, and then you come out with some sort of conclusion. Okay, so we learned all that, and so today, what we're going to do is basically solidify your understanding of proofs. Okay, we're gonna start with a couple of proofs, a couple of easy proofs, and then we're gonna go back in your book and learn all the principles, all the postulates, the theorems that you should know up to this in the first two chapters of your book, so that when you get questions, you'll be clear on what to do. Now, most of these postulates we've already covered, and you should know. So I'm going to be covering them not by lecturing, but by quizzing you and asking you if you know them. And I'll note some, I'll just jot them down by name. I may not write much about them. And then you're supposed to go back in your book and then find more information. Okay. So the first sample problem, let's look in your book and see if there's a nice problem. Okay, so like I said, we're going to do an easy proof. Let's see. Okay, here's a problem. Okay, so given that angle, I'm going to call this, what should I call this angle? Angle gamma and angle beta are a linear pair. Okay, prove that angle gamma and angle beta are supplementary. Okay, so before we actually solve the problem, okay, let's just review what a linear pair means. So the definition of a linear pair is two adjacent angles whose non-common sides are opposite rays. Okay? So this is one different opposite rays. So basically, before I can even sketch that, you need to remember what adjacent angles are. Do you remember the definition of adjacent angles?
Angle right next to another one?
Yes. So adjacent angles are angles that are right next to each other. And by, that means angles that share a common side, basically. So they share a common side, but they have two different interior angles. Okay, so they share a common, not interior angles, interior points. They share a common side, but have different interior points. Okay, so let me just draw. So angle 1 and angle 2. This is angle 1 and this is angle 2. Okay, angle 1 and angle 2 are adjacent angles. Okay, here's angle 1 and this is angle 2. They're adjacent angles because they share this common side. Okay, basically a common ray. They share a common ray, and but they don't share any interior points. The interior points of angle 1 are here. The interior points of angle 2 are here. So that's what makes them adjacent angles. Now, a linear pair are two adjacent angles where this is the non-common sides. This is one non-common side. This is one non-common side because this is a common side. So these non-common sides are opposite, okay? They're pointing in opposite directions. And so I'm going to draw a linear pair up here. So you might have point A, point B, and C. And then you have, okay, so this is your first angle, and this is your second angle. Okay, so these are adjacent angles. So given that, how do you prove that if you have two angles, angle gamma and angle beta, which are linear pairs, how do you prove that they're supplementary? I mean, and of course, remember what supplementary means, right? What's supplementary?
If those angles add up to 180.
Yes, okay, let me just write that. So definition of supplementary angles is they add up to 180 degrees. Okay, so those are basically the basics that you need to know. You need to know that definition. You need to know what adjacent angles and linear pairs are. And so you put all three together and you should be able to prove that. If angle gamma and angle beta are linear pairs, then angle gamma and angle beta are supplementary. So let's quickly see if we can do that, okay? Remember, when doing a proof, you do your step-by-step arguments, and then you do the statements on one side, and then you do the reasons. You have to give your justification, okay? So we're gonna prove this thing using a column proof where we have statement on one side and the reason on the right-hand side. So what did I say? Where do you begin in a proof? Do you remember?
No.
Oh, you start with the givens. Okay, you always start with the givens, and then you work off that and move forward until you get to your goal, what you're trying to prove. Okay, so again, you're given that angle gamma and angle beta are linear pairs. Okay, so prove that angle gamma and angle beta are supplementary. And it always helps to draw a nice diagram when solving any math problem. It really does. So I'm gonna sketch something here. I mean, if you can do this in your head, more power to you, but I can't. So, okay, so go ahead. Where do we start?
Get the unknowns.
Okay, first thing is we start with the givens. We say that angle gamma and angle beta are a linear pair. Okay, and that's given. The reason is given. Okay, so what's the next step? Okay, the next step is to say that the two rays. Now I'll give them a name. I'll say. So the two rays, BA and BC, form a straight line. Okay. So the two rays form a straight line. Okay, how do we know that? How do we know that the two rays form a straight line? Because that's the definition of a linear pair, right? Yeah. Okay, that's from definition of linear pair, right? Right. The non-common sides basically form our opposite rays. They form a straight line. Okay. So where do you suppose we go from there? When you're doing a proof, you always keep in mind where you're headed, where you're trying to get to. And where you're basically trying to get to is that these two angles add up to 180 degrees, okay, that they're supplementary, all right? You're trying to get to the fact that these two angles are supplementary, gamma and beta. Okay, so we've gotten to the point where we're saying that this is a straight line, basically, okay? That the non-common sides of the angles form a straight line. Okay, this is a straight line. So where do we go from there?
We solve it.
Okay, so it's a straight line, and then what's next? What do you say next?
Angle A and angle B equal 180.
No, you don't. You say that that straight line is 180. That straight angle is 180. Okay. So basically, ABC is 180. So angle ABC, the measurement of angle ABC equals 180 degrees. And that's by basically definition of a straight angle. Let me spell straight correctly. Straight angle. Okay, so we've made it to the point where we said this straight line is 180 degrees. What do we say next?
Both angles equal 180 degrees.
Oh, okay. And why do we say? You mean the addition of both taken together?
Yes.
Okay, so basically you're saying that measure of angle gamma plus measure of angle beta equals 180 degrees. Why do you say that?
Because A, B, and C equals, angle ABC equals 180 degrees.
Oh, okay. You're right, but this isn't really step 4. I would say there's one step before you get to that. Okay, how do you know that the measure of angle gamma, you really don't. All you know is that the entire thing is 180 degrees. Then all of a sudden you're jumping and saying that gamma plus beta is 180 degrees. There's one step that's missing, and this is a point about geometry. It's like you have to take baby steps. Okay, what's the missing step? Okay, we agree that the entire thing is 180 degrees. And then all of a sudden you're telling me that gamma plus beta is 180. What assumption did you make that you didn't say clearly, but that geometry requires you to say clearly? What tiny step did you skip over?
Gamma is supplementary with the other.
No, that's what you're trying to get to. Okay, I'll make it easy. Okay, you forgot that to say that gamma plus beta equals ABC. That's how geometry works. So you don't just jump and say the measurement of gamma equals this 180. First, you have to say the measurement of gamma plus measurement of beta equals the measurement of ABC. Okay, so measurement of gamma plus measurement of angle beta equals measurement of angle ABC. That makes sense, right?
Right.
Okay, and why can we say that? Okay, we didn't really cover this principle. It's angle addition postulate. Okay, so basically when you have two angles, basically when you have two adjacent angles, the overall angle, the measure of the overall angle equals measure of one angle plus a measure of the other. Okay, so that's the angle addition postulate. If you have one angle and then you have a ray that comes in between, splitting that one angle into two angles. So let's say you had one angle, which is ABC, and then you had a ray that's at the vertex, and that's in between the original angle. So that's this ray, and it splits the original angle into two angles. Then these two angles, the measure of these two, angle gamma and angle beta, adds up to the measure of the overall angle. So that's the angle addition postulate. Okay? So now we know that the measure of angle gamma plus the measure of angle beta equals the measure of angle ABC. So then we get to your point where you were saying that measure of angle gamma plus measure of angle beta equals 180 degrees. So how do we justify that? How do we justify going from step 4 to step 5?
I'm not sure.
Okay. Step 4 says that the two angles add up to angle ABC. Okay? But step 3 already tells us that angle ABC equals 180 degrees, right?
Right.
And so we can substitute 180 degrees wherever we see measurement of angle ABC, correct?
Correct.
Okay, so that's the substitution property. Okay, so we're using steps 3 and 4 for this substitution. Okay, so now we get that the two angles add up to 180 degrees. And so what's our final step in our proof that they're supplementary? So what's our final step?
Addition.
Okay, so we say measure of angle A plus measure of angle B equals 180 degrees. So we can say that, I didn't mean A and B, I meant alpha and gamma. So we can say angle alpha and angle beta are supplementary, okay? Just by definition of supplementary, okay? Definition of supplementary angles. Okay, definition of supplementary angles says two angles add up to 180 degrees. Then they're supplementary. So that's how you do a proof. As you can see, this is very challenging in that you need to be careful and justify why you're making every little statement. Why, as you're taking every little step, you need to be careful. Okay, so that's one proof. Let's do another one. I'm going to look for something in this other book. I have this very nice book that has a lot of good problems. So I'm going to try to get an easy, relatively easy proof problem. And let's see if we can work through that. Okay. Actually, I think before we do that next proof, it's better for you to look at this proof. Just look at it. Let's take a break. Look over this proof and make sure you understand and make sure you digest it and it makes sense. Then we'll do another proof, and then we'll go back in your book and do the postulates and basically the foundational principles and concepts that you'll need to do more and more proofs. Okay? So let's take a break for about 2 minutes so you can take a look at this and have it make sense. Okay.